in the reading on multiple regression, we've understood the core points, we've talked about dummy variables. A very testable aspect is the assumptions, and then more specifically the violations of the assumptions. So these are the assumptions of the multiple linear regression model, and I have highlighted some of those assumptions which are particularly important, especially when it comes to assumptions that might be violated. So one assumption is that there is no exact linear relation between two or more independent variables. Now, if this doesn't happen, then that's a violation. In other words, if there is a linear relationship between x1 and x2, two independent variables, then what is that called? What's that problem called? That problem is called multicollinearity. Okay? And we'll see this on the next slide, but since this is a review, you are expected to know this. The variance of the error term is the same for all observations. This is an observation, but if it is not, then the condition is called heteroscedasticity. And with heteroscedasticity, the issue is when we have conditional heteroscedasticity, where the variance depends on the x variable. And then this assumption is that the error term is uncorrelated across observations. If the error term is correlated, then what's that problem called? That's serial correlation. So those items are shown here. And what I have done is just given a summary of the three major problems that you need to look out for. In other words, whenever you run a regression, after running the regression, simplistically, what's the first thing you check? You want to make sure that the coefficients are significant. You want to make sure that the R squared is good. You want to make sure that the F stat is good. Once you've done that, then you also need to verify that the assumptions of the regression model are not being violated. And what are the three most important assumptions to look at? The first is check whether there's a heteroscedasticity problem. What's the heteroscedasticity problem? This is the problem that the variance of the error term is conditional on x. So if this is happening, that's a problem. How do you check for this? You check for this using the Bruch-Pagan test. If you do have heteroscedasticity, then F test is unreliable. So you might have a high F stat, but that doesn't mean anything. Remember this also, with heteroscedasticity, if this problem exists, the standard error will be underestimated, which means that the t-stat will be inflated. You don't need to remember both these points, because hopefully you recognize that when you come up with your t-stat, it's equal to the coefficient minus the hypothesized value divided by the standard error. So saying that the standard error is underestimated or understated is the same thing as saying that the t-stat is overstated. Then if we have the serial correlation problem, or if we think we have a serial correlation problem, how do we test for it? We do the Durbin-Watson test. And later, when we look at some problems, I'll talk about the Durbin-Watson test. I've seen this come up in several mock exams, so at least the basics of the Durbin-Watson test should be understood, and we will cover this. If you do have serial correlation, then the t-stat and the f-stat both will be too high. So can we automatically look at this and say most probably the standard error is understated? We can. And then multicollinearity, this is where two or more independent variables are highly correlated. And if you have this problem, here you have a high R squared, a significant F stat, but the issue is inflated standard error. So you will actually have low t-stat. So the t-stat being shown will be lower than what it should be. Remember that with heteroscedasticity and serial correlation, the t-stat is inflated, and with multicollinearity, it is understated. A major purpose of this crash course is to help you just remember the most important points. Model specification and errors in specification. When we say model specification, we are basically talking about the fact that in a regression equation, you have to define your dependent variable, and then you have to say what the independent variables are, coming up with the correct independent variables, and then using the appropriate transformations. That is model specification. Fortunately for us, we don't need to do the model specification on the exam. That's actually a hard thing to do. The model will be given to us. We'll just have to evaluate whether the model is good or not. You also might be tested on the principles of model specification. One principle is that there should be cogent economic reasoning. There should be an economic rationale for using particular independent and dependent variables. It should be parsimonious, which means that your model should have as few independent variables as possible. You should see whether there are any violations of regression assumptions, and a model is useful if it can be tested on out-of-sample data and it also works on out-of-sample data. Misspecified functional form. So what are the different ways in which a model can be misspecified? One or more important variables might be omitted. So that's one issue. One or more of the regression variables might need to be transformed, but you might not have transformed them. That's another issue. The regression model pools data from different samples that should not be pooled. So these are three possible issues. Time series related misspecification we'll see in the next reading, but I'd say that you try to remember these points. Coming now to the third and final reading in quantitative methods, which is time series analysis. When we talk about time series, very broadly speaking, we will either look at trend models or autoregressive models. A trend model is fairly straightforward. There we are saying that the x-axis is time, and we are predicting an output such as sales or some other variable based on time. So that's a trend. With a linear trend model, your x-axis is time and y-axis is just sales or some number. But with financial data, very often you will have exponential growth. So if you look at sales data, you might say that sales grows at a certain percent. So if you are saying that sales grow at 10%, it's always 10% of the previous number. And typically you will have exponential growth. So if you try to model exponential growth with a linear relationship, which problem clearly is happening over here? Of the three problems that we talked about in the previous reading, which one do you see over here? Heteroscedasticity, serial correlation, or multicollinearity? The biggest issue is serial correlation. Why? Because clearly the error terms are correlated. So notice these error terms. So if this error term is negative, you can tell that the next error term is also going to be negative. When the error term is positive, then the next error term is also positive. So there is a correlation between error terms if you have this sort of a model. If you are using a linear model to try and forecast sales, where sales are growing exponentially, you have an issue. So linear trends do not correctly model growth of a time series, and this is where you use log linear trends. And we've seen this in example 2 in the curriculum. All right, so with the log linear trend, what do? The x-axis is still time, but the y-axis is now the natural log of sales. And then notice that we have a much better model. You need to remember these facts. The regression model assumptions must be satisfied. Earlier, the serial correlation issue existed, so we have to do something to get rid of that issue. Error term correlation is often an issue when we do time series, so just know that. And you can carry out the Durbin-Watson test to figure out whether serial correlation is an issue or not. All right, coming now to autoregressive time series model. An autoregressive model is a time series where a given variable is regressed on its own past values. So notice this is the variable. There's only an x variable here because we are regressing x based on its own values in the past. In this scenario, we are regressing against one lag. In the second scenario, we are regressing against 2 lags. Or here it could be even 3, 4, how many ever lags. Some points to keep in mind. For autoregressive models to work, time series must be covariance stationary. And what are the 3 things that hold true when data is covariance stationary? Constant expected value, constant variance, and constant covariance. So remember this point. Another very testable point is that with AR models, the Durbin-Watson statistic does not work. It works under your regular regression. It works with trend models, but it does not work with AR models. Test whether the autocorrelations of error terms differ significantly from 0. So what are the tests that you need to do? Your null hypothesis is that the error autocorrelation at a specific lag is 0. So you are looking at the correlation of an error term with the previous error term. And then, so what is the null hypothesis? That the autocorrelation is 0. So this is a case where you actually want the null hypothesis to be true, because you want the correlation with previous error terms to be 0. If this is not the case, then you have a serial correlation problem. For these tests, you need to recognize that the standard error of the residual correlation is 1 over square root of t, where t is the number of observations, and your test stat is the residual autocorrelation divided by the standard error. Now stare at this for a minute, because I want you to remember this, and we'll use it on the next slide. So this is a sample output from an AR model. The R squared looks decent, the standard error is low, so this is number of observations. Durbin-Watson, is this going to be of any use to us? It's not, but the regression tool doesn't know exactly what we are doing, so it will give us the Durbin-Watson anyway. We ignore it. Now let's look at the data. So what is this part of the output telling us? It is telling us that our X value at a given time t can be predicted based on 1 lag. So the coefficient for that lag is 0.866. The t-stat looks good. Even the t-stat over here looks good. So can we happily move on, or do we also need to check for serial correlation? We need to check for serial correlation. And we do that over here. Notice that if you look at the serial correlation of error terms with 1 lag, then the t-stat is low. So this is okay. This is saying that the null hypothesis that the correlation is 0 is not being rejected, so that's good. What about with a lag of 2? So all these actually are looking reasonable. So none of these t-stats are very high, which means that presumably all the correlations with previous lags are 0, or not, statistically speaking, not different from 0. So this looks like a decent result. Okay, just a few miscellaneous points related to AR models. We can use the chain rule to forecast. Now what does this mean? You have an AR model. Can you predict the value of x at time t plus 1 based on the value of x at time t? Yes. Can you predict the value of x at time t plus 2? Again, you can do that based on x t plus 1. So, and then you can keep going. You can predict x t plus 3 based on t plus 2. So this is called the chain rule. That's point number 1 over here. Point 2 is that you need to understand the distinction between in-sample forecast errors and out-of-sample forecast errors. So for a model to be useful, it needs to be good at predicting in out-of-sample data, because you already know what sample data you have. So the sample data is used to create the model. A good model will help you when it is used with out-of-sample data. So if you have 2 models, model A and model B, the better model will do a good job of predicting the dependent variable in out of sample data. And the measure or the statistic that you use to see how good a given model is this thing, the root mean squared error. And a lower root mean squared error is better. The curriculum gives an example where this is calculated. If you have time, you can look at it. But at the very least, just remember that this is the measure to see which of your models is better. And then the third point, estimates of regression coefficients of time series models can change substantially across different sample periods used for estimating the model. When selecting a time period, first determine whether economics or the environment have changed, and second, look at graphs of the data to see if the time series looks stationary. If it does not, then you have an issue. All right, next point. Mean reversion, random walks, and unit roots. So I've taken a few related concepts, put them all on one slide. Let's say that you have this AR model. For an AR model to work, the variable X in this case needs to be mean reverting. Mean reverting means that it's not randomly going up or randomly going down. It has some value. Variables such as interest rates or inflation, for example, would be mean reverting. The mean reverting level is given by this formula. It's B0 divided by 1 minus B1. So here is another formula for you to remember. A random walk is a time series in which the value of the series in one period is the value of the series in the previous period plus an unpredictable random error. So this is a random walk. Sometimes you can have a random walk with a drift where there is some other non-zero term over here. But the key point with the random walk is that the coefficient B1 is 1. When B1 is 1, as we have with a random walk, with or without a drift, then the mean reverting level becomes undefined because you have B0 over 1 minus 1, which is undefined. When B1 is 1, then mean reverting level is undefined. This is a problem. The name of the problem is the unit root problem. So you need to remember that. If B1 is 1, then you have a unit root problem. Fortunately, this problem has a solution. That solution is first differencing, where you take the difference between consecutive numbers. And this is explained in detail in example 12 that we've done in our regular videos. So if you are not sure about this, make sure you go over it. But if you are quickly reviewing, then at least remember these problems and remember that the solution is first differencing. Next point has to do with seasonality. Very often we have time series data where the data is seasonal. So let's say that we are looking at this information. We have an AR1 model. AR1 model means that we are regressing just with one lag. All right, do the t-stats here look good? They do, because they are significantly greater than 2. Does the correlation with the first lag look decent? It does, because notice here the t-stat is small, which means that you cannot reject the null hypothesis that the correlation is 0. And that's actually what you want here. But when you look at this number, when you regress the error term with the error term 4 periods ago, then you have a very significant t-stat. So this is telling us that there appears to be a significant correlation between the error term and the error term 4 periods ago. So obviously in a seasonal business, your quarterly numbers will depend or have a relationship with the number 4 quarters ago. So same time last year. How do we solve this problem? By adding another X value. So we are already regressing against T minus 1, previous period. We also now need to regress with T minus 4. So we need to regress with x minus 4. So we need an AR4 model. And look what happens when we do that. If we have lag 1 and lag 4, the t-stats are all significant. And look at these t-stats now, where we do the autocorrelation of the residuals. These are all much less than 2. So that says that the autocorrelations now appear to be 0. So the error terms are not correlated. And now the serial correlation problem seems to have gone away. So that is a good thing. If you have time, go over these examples. All right, regressions with more than one time series. Very often in finance, you are regressing multiple time series data, and the classic scenario is where you find the beta of a stock. To find the beta of a stock, you are regressing the time series of returns of the stock with the time series of returns of an index such as the S&P 500. So what do you need to be careful about? If linear regression is used to model the relationship between two time series, a test should be performed to determine whether either time series has a unit root. Okay, so is unit root a problem? So far we've said that it is. If we have a unit root which is where B1 is equal to 1, then the mean reverting level is undefined. So keep this in mind. If you have time series A and B and either has a unit root, if neither has a unit root, so there is no unit root problem here, no unit root problem here, then we can use linear regression. So that's okay. If one of the two series has a unit root, so this has a unit root problem, but this is okay, then we should not use linear regression. Okay, so if either one is problematic, you cannot. What if both have a unit root? If you think about stock market returns, for example, or think about any variable, if both these time series have a unit root, then can we use linear regression or not? The answer is that it depends. Depends on whether these two time series are co-integrated. Co-integrated means they are related to the same macro variables and follow similar trends. So unit root problem on both sides, but as long as they are co-integrated, which means that they react in the same way to similar economic variables, then we can. If they are not co-integrated, then we cannot use linear regression. So the next question then becomes, how do we test whether the data is co-integrated or not? And here we do the Engel-Granger test, also called the Dickey-Fuller test, for co-integration. So here, if we can reject the null hypothesis that the error term has a unit root, then we conclude that the two time series are co-integrated. So just remember, actually core point to remember is that if they are co-integrated, then you can use linear regression, and you use the Dickey-Fuller test to determine whether they are co-integrated or not. All right, we are nearly done. What I have done over the next few slides is just reproduced a summary from the reading, which talks about suggested steps in time series forecasting. So these are the steps. I would encourage you to read them. They are also part of a regular lecture. Okay, now in 3 slides, what I have done is summarized the most important formulas, and I've looked at questions in the past, and I've not reproduced all the facts and definitions, but on 3 well-spaced slides I've reproduced all the important formulas. So with correlation, this is the formula. You need to come up with the t-stat, and what is the null hypothesis? It is that the correlation is 0. If you come up with a correlation based on a sample, and this statistic is greater than 2, that means that you can reject the null hypothesis that the population correlation is 0. So key to remember this, r into square root of n minus 2, where n is the number of observations and r obviously is the correlation from the sample. Okay, then we come to regression. This is your basic regression equation. B1 is your coefficient. What is the confidence interval for the coefficient? It's B1 hat. B1 hat is the value that's coming from your regression. So the hat means it's an estimate coming from the regression, plus or minus TC. TC is the critical value. If you are using a 5% significance, then this will be approximately 2. And then what is this? This is the standard error. And where will this come from? This will come from your regression. If the standard error is not given and the t-stat is given, you can use the t-stat to come up with the standard error. We've done that. Okay, so this is the formula from level 1. What's the t-stat? It's the estimated value, this you will get from the regression, minus B1, which is the hypothesized value. Your regression output generally assumes that this is 0, and this is the standard error. So all this actually is level 1 stuff. You did this in the reading on sampling and estimation. Alright, prediction interval for the regression equation. This is the overall regression equation, and again this is fairly straightforward. This is the predicted value of the dependent variable based on the regression. Wherever you see a hat, that means it's the predicted value. TC is your critical value for a 95% confidence or 5% significance. This will be approximately 2. And then SF is the standard deviation of the prediction error. The way the curriculum puts it is it's the square root of the variance of the prediction error, but I think it's simpler to simply think of it as the standard deviation of the prediction error. So notice that this SF is different from the SB1 hat. This SB1 hat refers to the standard error related to the coefficients. This SF refers to the error associated with the overall prediction made by the regression equation. All right. Then you need to know the formulas for R squared. R squared is simply the explained variation over total variation. And this formula makes it clear that a high R squared is good. So if you have a high R squared, that means that your regression equation is doing a good job of explaining the dependent variable based on the independent variable. The third error-oriented term is this. And one of the confusions with quant is the number of terms that you need to grapple with. So remember, just to make sure you are with me here, the first error term was related to the coefficients. Then there is an error term related to the prediction of y hat. And then there is this third error term which is called the square root of the mean square error, SEE. This is the formula that we had. And how do you come up with this? Using the ANOVA. In the ANOVA you will have the square root of the mean square error. This was in the second row. So you pick it up from there and find the square root. Okay, this is the overall formula. Generally a low SEE is good and a high R squared is good. You also need to know the formula for the F stat. This is the regression, the mean regression sum of squares divided by the mean square error. So this overall thing is the mean square error. And what does the F test? It tests this null hypothesis that all the slope coefficients are 0. And you ideally want to reject this null hypothesis. When you reject this null hypothesis, that is saying that the slope coefficients are actually telling you something. And then we have the Durbin-Watson statistic for correlation. Remember this formula, and I'll just very briefly illustrate this formula, but then we'll talk about it in more detail with an example. Let's say that you have an output where the Durbin-Watson statistic is given as 2. So if Durbin-Watson is 2, you plug in 2 over here. So 2 is approximately equal to 2 into 1 minus r. What must r be? For this to hold, r must be 0. So if the Durbin-Watson statistic is 2, that means that the correlation is 0, and we do not have a serial correlation problem. What if, just let's take another scenario, if r is equal to 1, then do we have a serial correlation problem? We clearly do, because this is as highly correlated as we can get. So if r is 1, then what do you have? You have 1. If r is equal to 1, then the Durbin-Watson statistic will be 0. And what if r is minus 1? So if r is 1, Durbin-Watson is 0. If r is minus 1, then Durbin-Watson will be 4. So notice that Durbin-Watson is on a scale from 0 to 4. If Durbin-Watson is 2, that means we don't have serial correlation. If Durbin-Watson is 0, that means we have very positive serial correlation. If Durbin-Watson is 4, that means we have very significant negative correlation. So remember this formula and remember the facts that I have just given you. All right, the third and final part of the formula sheet. When we are doing AR models, to test whether the autocorrelation of error terms differs significantly from 0, we do this test. The null hypothesis is that the error autocorrelations at a specific lag are equal to 0. The standard error of the residual correlation is 1 over root t, where t is the number of observations, and the test stat is the residual autocorrelation divided by the standard error. And all this will be given in your regression output. If you have an AR model like this, this is the formula for the mean reverting level. Remember that. And when you have a unit root problem, then you need to take a difference, and this is called first differencing. So that is it. As always, practice a lot. To get the most out of this crash course, I would strongly encourage you to do the questions that I have asked you to do. And as you saw over here, in a short while, I have captured the most important points from Quant. I can't guarantee that what you will get on your exam will be from here, but I can say with reasonable confidence that we've covered the most important points. So probably 80% of what you will get has been covered. But always the key is that you practice a lot.